Hello and welcome back to Introductory Astronomy. Last time we were discussing the possibility of the universe expanding forever or the universe collapsing. In order to answer this question, we need to figure out the actual density of the universe. Now, measurements of luminous matter suggest that the actual density is only a few % of the critical density. But we also know that there must be large amounts of dark matter. But even when dark matter is taken into account, using the best estimates for its existence that is needed to bind galaxies in clusters and to explain the gravitational lensing that we observe, it still only amounts to an observed density of only 3/10 of the critical density. It seems very unlikely that there could be enough dark matter to make the density critical. So astronomers use type 1 supernovae to measure the behavior of distant galaxies and try and figure out whether we live in an expanding or decelerating or accelerating universe. Now, if the expansion of the universe is decelerating, so it's slowing down, which that would be the case if the force of gravity was the only force acting, then the furthest galaxies had a more rapid recessional speed in the past, and will appear as though they were receding faster than Hubble's law would predict. So let's take a look at actual observations of distant supernovae. This is data of around 50 supernovae, and they strongly suggest that the cosmic expansion is accelerating. As you can see, in a decelerating universe that corresponds to a purple and the red curves, redshifts of distant objects are greater than would be predicted from Hubble's law, the black curve. The reverse is true for an accelerating universe. The vertical scale here shows redshift. For small velocities, redshift is just velocity divided by the speed of light. So when we look at this data, we see that they correspond not to a decelerating universe, but to an accelerating one. And this acceleration cannot be explained by current theories of the universe, although we do know that it is not caused by either matter or radiation. The bottom frames show 3 of the above graphed supernovae marked by arrows that exploded in distant galaxies when the universe was nearly half its current age. The top frames show the same areas prior to the detonation of those supernovae, which were originally discovered in 1997 during a ground-based survey with the Canada-France-Hawaii telescope on Mauna Kea. Let's take a look at this figure. As illustrated here, the repulsive effect of what we call dark energy is proportional to the size of the universe, so it increases as the universe expands. Now you may ask, what is dark energy? Well, nobody actually knows. It is one of the leading puzzles in astronomy today. Whatever it is some kind of mysterious cosmic field that causes the universe to accelerate, and we know it's not matter or radiation. We do know that whatever it is, it was negligible at early times, but today, given the magnitude of the observed acceleration, it is a major factor controlling the cosmic expansion. Also, since the effect of gravity weakens as the expansion proceeds, it follows that once dark energy begins to dominate, gravity can never catch up, and the universe will continue to accelerate at an ever-increasing pace. Therefore, despite the considerable uncertainty as to the nature of dark energy, we can at least say that by opposing the attractive force of gravity, dark energy's repulsion strengthens our earlier conclusion that the universe will expand forever. Einstein and the cosmological constant. Your book goes over this at great length in Discovery 26-2. The cosmological constant, or vacuum energy, was originally introduced by Albert Einstein to prevent general relativity from predicting that a static universe would collapse. That was the idea at the time, that the universe was static. When the universe turned out to be expanding after Hubble's work, Einstein removed the constant from his theory, calling it the biggest blunder of his career. But now it seems as though something like a cosmological constant may be necessary to explain the accelerating universe, what we call the dark energy. Again, we still don't really know what dark energy is, and there's a lot of work that needs to be done in that area. So what supports this dark energy theory? In the early life of the universe, the geometry must be flat. The assumption of a constant expansion rate predicts the universe to be younger than what we observe. This graph of size of the universe versus time in billions of years now includes the case of the accelerating universe. Given what we know now, the age of the universe works out to be about 13.7 billion years. And of course, you can see the difficulty in figuring out the scenarios because we live in a point where present time corresponds to a lot of possibilities because all the curves meet at that same point. But based on the data we have, we believe that the universe is accelerating. So we believe that we live on the green curve. The age of a universe without dark energy is represented by all three lower curves, and is always less than 1 over h0 and decreases for larger values of the present-day density. The existence of a repulsive cosmological constant, or dark energy, which corresponds to the green curve, increases the age of the cosmos. And this is consistent with other observations, particularly of the age of globular clusters, and yields the following timeline. Approximately 14 billion years ago, we had the Big Bang, which, by the way, it was neither bang and there was no bang. It wasn't big because it was infinitesimally small, right? A singularity. And there was no bang because there was no matter around for sound to travel through. 13 billion years ago corresponds to the age of the quasars, and about 10 billion years ago corresponds to when the first stars were formed. Which brings me to cosmic microwave background radiation. It was discovered by accident in 1964 as two researchers tried to get rid of the last bit of noise in their radio antenna. Instead, they found that the quote-unquote noise came from all directions and at all times and was always exactly the same. They were detecting photons left over from the Big Bang. Of course, they didn't know that at the time. What you see in the picture is the sugar scoop antenna, which was built to communicate with Earth-orbiting satellites and was used by Robert Wilson on the left and Arno Penzias to accidentally discover the 2.7 degree Kelvin cosmic background radiation. Now, when these photons were created, it was only 1 second after the Big Bang, and they were very highly energetic. The expansion of the universe itself has redshifted their wavelengths so that now they are in the radio spectrum with a blackbody curve corresponding to about 2.7 Kelvin. Think of the two-dimensional analog with the balloon we talked about last time. As the balloon expands, the wave on the balloon gets a bigger and bigger wavelength, gets longer and longer. So it's the exact same idea. In this picture right here, we have cosmic blackbody curves. In A, we have 1 second after the Big Bang. In B, 100,000 years after the Big Bang. In C, 10 million years after the Big Bang. And D corresponds to today, approximately 14 billion years after the Big Bang. The intensity of the cosmic background radiation, as measured by the COBE satellite, agrees very well with theory. The curve is the best fit to the data, corresponding to a temperature of 2.725 Kelvin. The experimental errors in this remarkably accurate observation are smaller than the dots representing the data points. And here we have the COBE map of the microwave sky that reveals that the background, the microwave background, appears slightly hotter in the direction of the constellation Leo and slightly cooler in the opposite direction. The maximum temperature deviation from the average is about 0.0034 Kelvin, which corresponds to velocity or 400 kilometers per second in the direction of Leo. So as you can tell, the temperature of the cosmic background radiation is pretty even. Let's talk a little bit about what we think the contents of the universe are. Now, visible matter, what we can interact with, corresponds to about 4% of everything in the universe. Dark matter, the matter that we know is there because we can see its gravitational effect, but we can't directly see it, corresponds to 24%. And dark energy, this mysterious repulsive force, corresponds to 72%. So we only experience about 4% of all the mass and energy in the universe. The nature of the rest of it, 96%, is totally unknown and mysterious. Here's a little summary of chapter 26. On scales larger than a few hundred megaparsecs, the universe is homogeneous and isotropic. Our universe began about 14 billion years ago in a cataclysmic event called the Big Bang. The future of the universe, it will either expand forever or it will collapse. Density between expansion and collapse is the critical density omega naught. A high-density universe has a closed geometry. A critical universe is flat, and a low-density universe is open. Luminous mass and dark matter make up at the very most 30% of the critical density. The rest is dark energy. Acceleration of the universe appears to be speeding up due to this form of dark energy, and this is based on our observations. Cosmic microwave background is photons left over from the Big Bang that now correspond to a blackbody curve of 2.7 degrees Kelvin. Study chapter 26.4 through 26.8. Be able to describe the relationship between the density of the universe and the overall geometry of space. Explain why astronomers think the expansion of the universe is accelerating, and discuss the cause. Be able to explain what dark energy implies for the composition and age of the universe. and also describe the cosmic microwave background and explain its importance to the science of cosmology.